Good afternoon. Today we have the opportunity to speak with two scientists who changed the way we understand energy. In the mid-19th century, science was still rife with debate. Many accepted the caloric theory, which considered it had to be an invisible fluid. It was unknown how energy was transformed or conserved. In this context, two very important figures emerged. Julius Robert von Mayer, a German physician, and James Prescott, an English physicist. Mayer was born in 1814 in Heidelberg, Germany. From a young age, he excelled in mathematics and natural science and studied medicine, but was always curious about physical and biological phenomena. During his voyages as a doctor on ships, he observed how human bodies reacted to different climates, which led him to formulate revolutionary ideas that would change the way we think about energy. Jules was born in 1880 in southern England. From a young age, he was interested in electricity and physics, and although he worked in the family library, he devoted time to scientific experiment. His research made it possible to practically demonstrate that mechanical work can be converted into heat, supporting Mayer's hypothesis. Dr. Mayer and Mr. Jules, thank you for joining us. To begin, could you tell us what science was like at the time and obstacles you faced?
Science was dominated by traditional ideas. The caloric theory was accepted by the majority, and questioning it was very complicated. My challenge was to observe simple phenomena and deduce a law that applied to all systems, without having a formal position in physics.
In my case, I need concrete, reliable evidence. Many physics though that mechanical work could be transformed into heat. That's why I designed experiments to accurately measuring energy in different forms. Experimental evidence was essential to convince the scientific community.
Dr. Mayer, tell us how your idea about the conservation of energy came about.
During voyages and ships as a doctor for those ships, I observed that a sailor's blood changed color depending on the climate, whether it was red in the tropics or paler in the cold places. This indicated that a human body needed to produce more or less heat depending on the external temperature. I reflected that heat couldn't appear out of nowhere. It had to come from another form of energy, such as chemistry or food. This led me to propose that energy is conserved and transformed, a principle valid for all the systems.
Was it difficult for your colleagues to accept this idea?
Yes, many rejected it because I was a doctor and not a physicist. Furthermore, the idea went against the dominant caloric theory, which everyone already knew and accepted. However, I treated my observations as experimental evidence to support it.
Can you explain how you relate your biological observations to a universal principle of physics?
Of course. I observed that the energy consumed by the body in activities and heat didn't disappear. It was only transformed into heat or mechanical work. This made me think that the same rule should apply to all physical phenomena. Energy isn't lost, it only changes form.
Mr. Jules, you experimentally verified Mayer's hypothesis. How did you it?
I decided to design an apparatus in which weights fell and rotate patterns inside a container of water. I measured the temperature of the water several times. Each time, the temperature increased exactly in proportion to the mechanical work performed. This demonstrated that work was transformed into heat.
How important was this experiment for the science of its time?
It was crucial because it demonstrated that the heat is not an invisible fluid, but rather energy that can be transformed and measured. It also allowed us to establish an equivalence between mechanical work and heat energy, providing concrete evidence that confirmed Mayer's hypothesis.
With this, my theory gained experimental support and arguments, since the combination of observation and measurement made it possible to establish the law of conservation of energy as a universal principle.
So, thanks to you, science went from assumptions to measurable evidence about energy. Let's talk about the knowledge that emerged from your work.
Well, thanks to the entire process, we want to demonstrate that energy doesn't disappear, it only changes form. This allowed us to understand vital processes, such as the transformation of food into energy and heat in the human body.
It was also fundamental to engineering and technology as it allowed us to design more efficient engines, electrical systems and factories, and provide the foundations of modern thermodynamics. Without this principle, many scientific and technological advances would not have been possible or as efficient as we know them.
Can you give concrete examples of how this law changed everyday life in your time?
Yes, it was possible to calculate the amount of energy needed to drive machines, heat homes, and improve the efficiency of industrial processes. It was even applied in nutrition and medicine to better understand metabolism.
Furthermore, it made it possible to predict how energy is transformed in electrical systems, steam engines, and chemical processes, connecting science with practical applications that improve society.
Today, the law of conservation of energy is still valid and present in our daily lives. Electric cars, solar panels, nuclear energy, the electricity we use at homes, and human metabolism all depend on the efficient transformation of energy. Dr. Meyer, Mr. Jules, thank you very much for sharing your discoveries and teaching us. Your contributions not only transformed the science of your time, but they continue to guide our knowledge in everyday life. Thanks to you, we understand that energy is continually transformed without being lost, and that its principle remains essential to science, technology, and our daily lives.